We talked about pH in an earlier unit, but let's cover it one more time. pH scales are what we use to measure how acidic or how basic or how alkaline. It usually goes from 0 to 14 to represent the relative strengths of an acidic or basic solution. pH stands for the power of hydrogen, or concentration of hydrogen ions, measured in moles per liter, and now we know what that means. So remember, this square bracket is referring to the concentration of H plus in mole per liter. Okay. It's an inverse relationship. That means as one of the compounds goes up, for example, as the concentration of hydrogen ions increases, the pH will decrease. Or as this concentration of hydrogen decreases, pH increases. The formulas that we've used before, pH is equal to the negative, and that negative sign is hugely important. The negative log base of 10, don't worry about that, your calculator assumes that you're talking about log 10, concentration of hydrogen, or if you want concentration, it's 10 to the, again, insanely important negative pH. Pure water itself does split into ions a little bit, very, very weakly. Not every single one, 1 in 100, 1 in 1,000, whatever you want to say. One water molecule and another water molecule. This water molecule will lose one of its hydrogens. This water molecule will pick it up. We'll have H3O+, this is the hydronium, and we've got hydroxide. Hydronium cation, hydronium cation, and hydroxide. Okay. Pure water will have a concentration of hydronium equal to 1.0 times 10 to the negative 7. That means it has a pH of 7. Hydroxide, the concentration of hydroxide will be the same. For every 1 hydronium, we'll have exactly 1 hydroxide. So that means the power of hydroxide is also 7. Pure water is said to be neutral, or pH 7, because the two concentrations are equal. So it's neither acidic or basic, it's right in the middle. In an acidic solution, the concentration of hydrogen goes up above the concentration of hydroxide, or the hydroxide concentration goes down, so relatively this is larger, but something stays the same. If you multiply the two concentrations together, the concentration of H plus and the concentration of OH negative, you will always get a number of 1 times 10 to the negative 14. Always, always, always. Similarly, in basic solution or an alkaline solution, either the concentration of hydrogen has gone down or the concentration of hydroxide has gone up, but if you multiply the two together, you always get the same. And the formulas for hydroxide are similar. The power of hydroxide is equal to the negative log. And if you want to calculate the concentration of OH, it equals 10 to the negative POH, just as it does for concentration of H plus. Those two facts together give us this very important relationship. Of any one substance, the pH and the POH both add up to 14, always. Always, always, always. So, every time that you have pH changing by 1 on that scale, it really means that it's 10 times a change in concentration. You can change concentration by diluting, adding water. Or you can neutralize, having the H plus and the OH negative, adding in whatever one you need to make water. two different ways of adding extra water. So we're going to go back and do some more pH calculations. This time, since we've talked about significant figures, we're going to incorporate significant figures into the calculations, but they're a little bit weird when we're using log formulas like this. It doesn't follow the rules that we've talked about before. In this case, the number of decimal places in the pH is equal to the number of significant figures in the question. So that means that first digit doesn't actually count as a significant figure. Let me show you how that works in a few examples. So this is a chart we've done before. Neutral is the easiest one to identify. Here we have some examples of compounds with different pHs. Neutral has a pH of 7. And the way this chart works is as we go more acidic, we get lower pHs all the way up to 0. And as we go down, we get higher pHs, 8, 9, 10. All the way up to 14 at the bottom. To get POH, well, if I take this formula, I know that pH and POH always add together to make 14. So if I want POH, it must equal 14 minus pH. 14 minus 0 equals 0. 14 minus 1 equals 13. 12, 11, 10, 9, 8, 7, 6. 7 and 7 should match up. Oops. 6, 5, 4, 3, 2, 1, and the last line should be 0. Now, how do we get these last two? Well, there's a formula. To get the concentration of H plus is equal to 10 to the negative pH. 10 to the negative 0 is equal to 1. 10 to the negative 1 is equal to 0.1. 10 to the negative 2 is equal to 0.01. 10 to the negative 4. 1, 2, 3, 4. 10 to the negative 5. 1, 2, 3, 4, 5. And I'm starting to run out of room. Maybe I can do 6. Okay, 10 to the negative 6. 1, 2, 3, 4, 5, 6. 10 to the negative 7. 1, 2, 3, 4, 5, 6, 7. I give up. I'm going to start using scientific notation. 1 times 10 to the negative 8. And the last one to negative 14. Alright, to get the concentration of OH, we know that this number multiplied by this number have to equal times 10 to the negative 1, or we can go based on the POH. Either way. Let's do it the same way we did these ones. The concentration of OH negative is going to equal 10 to the negative POH. So I'm going to get 1 times 10 to the negative 14. Cool. Alright, let's try some questions. Let's see. As pH increases, As pH gets larger and larger and larger, the strength of the base, we get more and more basic, it increases. Conversely, the strength of the acid, as we go up, decreases. As the pH decreases, the strength of the base, as pH decreases, the strength of the base decreases. And the strength of the acid increases. A solution of a pH of 2 would be very acidic solution, whereas a pH of 5 would just be slightly acidic. A pH of 8 would be slightly basic. Whereas 13 would be very basic. A solution of pH 3 is how many times more acidic than 5? Well, let's see. 3, 4, 5, we had to take 2 steps. Each step is 10 times bigger. So 10 times 10, it's 100 times. Whereas a solution of 12 is how many times more basic than a pH of 9? 1, 2, 3, 1,000 times. So let's try some concentration calculations with pH. Find the pH of a 0.02 mole per liter solution of HCl. So we need to think about this for a second. For HCl, put it into water, and it's going to ionize and make H plus and Cl negative. Every 1 molecule of HCl will produce 1 ion of H plus and 1 ion of Cl negative. So this means that the concentration of HCl will be equal to the concentration of H plus. So when I say that the concentration of HCl is 0.02 mole per liter, then I know that the concentration of H plus must also be 0.02 moles per liter. On my calculator, I hit negative log 0.02, and I should get 1.7. Sometimes your calculator will want you to do this backwards. 0.02, then the log button, then hit the negative sign, which isn't always the same as the subtract sign on your calculator. When I take a look at this question, I see that I have 2 significant figures, 1 and 2. So my answer should have 2 significant figures, 1 and 2. Remember, according to the crazy pH rules, the first digit is not a significant figure. Let's try a different one. What's the pH of a 0.05 mole per liter HCl solution? pH is equal to negative log concentration of 0.05 equals 1.3010299996. And my question, I've got only 1 significant figure. So that means my answer should only have 1 significant figure. What about going backwards? What if I give you a I give you a pH, I want the concentration. Instead of using the log formula, I use a different formula. If I want the concentration, it's equal to 10 to the power of negative pH. My pH is negative 1.7. 10 to the negative 1.7 gives me 0.02. So take a second, complete the following chart, pause the video if you will. I'll post up the answers in just a minute. So here are the answers. Fairly straightforward other than that last one. This last one is a trick because it tells you the concentration of a base, but asks you for pH. So you're going to use the pOH formula, negative log concentration of the base. Will give you 1.7 as your pOH, your power of hydroxide. To get your pH, you're going to do 14 minus 1.7 to get 12.3. Other than that, no other tricks. 2 more examples, and then you're free. Sodium hydroxide solution is prepared. A sodium hydroxide solution. This is one of our bases that split Na and OH, become aqueous. They ionize and dissociates into 2 ions. We're dissolving 6 grams in a volume of 1.00 liters. We want to know the pH, and the pOH. So, step 1. I need the concentration of NaOH in moles per liter. Alright. So, I have mass. I want molar mass of NaOH. Anytime of giving mass, I want the number of moles. So, sodium plus oxygen plus hydrogen, 40. So that means my number of moles is equal to mass divided by molar mass. That is 6, 40. .15 moles of NaOH. Well, that's not concentration. Concentration is equal to moles divided by volume. 0.15 mole, and I've been told that it's 1 liter. 0.15 moles per liter. Step 2. I want to know what the concentration of hydroxide is. I can take a look at my balanced chemical equation. Every time sodium hydroxide hits the water, it's going to dissociate. It's going to split into its 2 ions. Hydroxide is one of the ions. Every 1 NaOH donates 1 OH to solution. The concentration of NaOH is going to equal the concentration of OH. Therefore, the concentration of OH is going to be 0.15 moles per liter. For step 3, I want to know, in this case, since I have the concentration of hydroxide, I'm going to get the power of hydroxide, pOH. pOH is equal to the negative log of the concentration of OH, negative log of 0.15. .8239 to get pH. That's going to be 14 minus pOH, 13. In my question, I was told only 2 significant digits. The pH is 13.18 and the pOH is to 2 significant digits, 0.82. The last question says 1 milliliter of 1 mole per liter HCl is diluted to 500 milliliters. What's the new pH? So for number 2. I have a dilution problem. My initial concentration is 1.0 mole per liter. My initial volume is 1.0 milliliters. My final volume is 500 milliliters. I would need to know what my final concentration is, and I'll use that concentration to figure out my pH. Formula for dilution, C1V1 equals C2V2, or in this case final. I've got 1.0 mole per liter. In this case I can leave it as milliliters because both of the volumes are in milliliters. It won't matter. If you change them both to liters, you won't have any problems either. You just have an extra step. So that leaves my final volume as 1 milliliter divided by 500. So divide both sides by 500 milliliters. Milliliters and milliliters cancel. This is the reason why we didn't need to change everything to liters. When you put that in the calculator, you get 0.002 moles per liter. So this is telling us that our concentration of HCl is 0.002 moles per liter. I know that HCl dissociates and ionizes completely when put into water because it is a strong acid, so that tells me that my concentration of hydrogen ions is the same as the concentration of HCl, 0.002. If I want to know the pH, well, pH is equal to the negative log of the concentration of H plus negative log 0.002 2.698970. In my question, I've only really got one significant figure, so my pH is 2.7. You've got a few questions to try in the textbook, practice, and ask me questions tomorrow. Thanks.